Hi, I'm Daniel Alber, a medical student at NYU. Today I'll be presenting our project, evaluating the quality of salvaged blood products using stimulated Raman spectroscopy and deep learning. In this project, we use self-supervised learning to evaluate red blood cell morphology and suitability for blood transfusion. First, I'll talk about Raman spectroscopy and red blood cell transfusion. Then I'll go over our deep learning approach and results. And finally, talk a bit about some final thoughts and future work. Stimulated Raman spectroscopy offers fast, label-free imaging of tissue specimens right in the operating room at the point of care. It's been used to diagnose cancer in the OR, but to our knowledge has not been previously used for liquid samples. Intraoperative blood salvage using a cell saver or other device recycles blood lost during surgery. However, lab values taken after surgery suggest red blood cells are damaged during the salvage process, and no assay exists to determine whether or not these samples are safe for transfusion. We compiled a dataset of 36 blood samples, including both baseline preoperative and post-salvage blood samples, and then segmented more than 350,000 individual red blood cells. These hundreds of thousands of cells were fed into a ResNet-50 convolutional neural network and trained with the SimCOR self-supervised approach. We then performed supervised fine-tuning with 7,500 manual labels of normal or abnormal blood cell morphology, as you can see on the bottom right. Normal cells are biconcave discs. Abnormal cells have spikes or other strange projections. The results of our fine-tuning achieved an accuracy of more than 85% and an area under the curve of more than 90% for determining or predicting abnormal or normal red blood cells. Furthermore, we were able to predict lab values, such as mean corpuscular volume, closely to the ground truth obtained by standard lab assays. A t-SNE plot of the embeddings of blood cells from our pre-trained self-supervised network showed that normal cells cluster together, and heavily deformed blood cells also cluster together on a different side of the plot. Furthermore, most of the heavily deformed blood cells come from the cell saver, or our salvaged blood cells. In conclusion, we applied self-supervised learning to evaluate red blood cell morphology and its suitability for blood transfusion. We categorized deformed blood cells using a pipeline of stimulated Raman spectroscopy and deep learning that in total can analyze a blood sample in under 90 seconds. We determined there were variations between salvaged and unsalvaged blood. Salvaged blood, which increases complications after surgery, had many more deformed cells. Our future work will aim to develop an embedding-based benchmark of red blood cell deformity, measuring the distance between salvaged and baseline blood samples, and analyzing whether outcomes differ when it's above a certain threshold of difference between the two samples. Thank you.